Well, ladies and gentlemen, we're ready to start now. So welcome to the round table. We have up to an hour. We will have the following format, if we may, that I'll invite the four people on the panel to make an initial statement of up to 2 minutes, which can include questions to one another, and then there'll be a free-for-all. But they won't get to answer each other's questions until we've heard something from you all. So I'll try to gather themes a bit, and I would like to just mention that the order will be first Simon, and then, as I remember rightly, Antony, then Carlo, then David Wallace. So Simon, off you go.
Okay, right, thank you. I think I have really more of a question than a comment. And it's directed to Carlo. It does seem to me that the nature of this series of talks and the discussion is the relevance or lack of it of quantum foundations to cosmology. It does seem to me and to many others that cosmology presents an extreme challenge to conventional interpretations of quantum theory, and in particular, whether it be Copenhagen or conventional measurement postulates, quantum mechanics. Carlo is denying that, and this seems to me somewhat at the crux of the affair. Now, as I understand it, and this may be wrong, Carlo's picture of the quantum state as involving information, and therefore, in principle, not being applicable to a single system in isolation from any other, and therefore not applicable to the universe as a whole, would suggest that the state in itself, either it is not representational, or if it is representational, then it's, and correct me if I'm wrong here, somebody's representation. Now, if it's not representational, then I do think, I don't quite have my list. I have my 3 pillars. I also should throw in decoherence theory. The claim is the evident interpretation follows from those 3 pillars. Galileo's dictum about how to analyze the process of observation, Dennett's criterion for when to count something as real, McIntyre's principle that things are fundamentally processes. I throw in decoherence theory. If I do that with Wojciech Zurek, actually, then you see very well why Occam's razor doesn't work here. All of these people, there's too many beards. But anyway, I come back to Galileo's directive. Let me just read it out. To find out things will look like, according to a physical theory T, represent the observation process itself, and if need be, the observer, in that theory T, along with the things observed. Okay, so even if you insist, so either you say that there is no representations available in quantum mechanics at all, and then it seems to me that's flatly not in keeping with scientific practice, and calls out for some other theory that is representational. Or, if it's going to be somebody's representation, why can that representation not be a representation of the world, including that very person who is doing the representing? In other words, it is perfectly appropriate, indeed typical of physical practice. Galileo, when considering why is it that we don't see the Earth moving, Wittgenstein made this very nice question, what would it look like if it did look like the Earth went round the sun? So Galileo, in addressing this question, why don't we see whatever, a huge wind or so forth, he put himself, not just anybody else, he put himself into the picture, into the world. Principle of inertia, they all move together. So why can I not do that? Even if the representation is only somebody's representation, then let it be my representation, let it be of the universe and myself in that universe. And then I want to know by what principles, by what rules, by what laws, the subsequent development of that relation between myself in the representation and the world change in time. Now, presumably, there is going to be a flat dictum that you just can't do that. And I don't understand that dictum. I don't understand why somehow that is ruled out. That's being inappropriate. So.
Hold that thought. Antony, you're next, my friend.
Carlo, sorry, I'm going to pick on you first as well. But don't worry, because it's going to be short, and then I'm going to pick on these guys. So, going back to the question I asked, I think yesterday. So, maybe you weren't sure whether to come here and accept the invitation to speak here or not. You did the following. You looked at it. You measured the spin of a particle, and you said, "Okay, I'll do this. If it comes out spin up, I'll accept. Comes out spin down, I won't accept." There's some superposition in a quantum state of these two outcomes. Some super observer, some advanced extraterrestrial, millions of years in advance, more advanced than us in technology, carries out an interference experiment on these two branches, and for him, there is no fact of the matter as to whether we're having this conversation or not, because for him in his experiment, these two possibilities interfere. Now, as I asked you, you confirmed that in your view, this is correct. For him, there is no fact of the matter about whether we're having this conversation or not. Now, I would just ask, bluntly, well, look, this is a super intelligent being, much more intelligent than us, and he does not believe that we're here having this conversation. And it's not just that he doesn't believe it. In your view, it is a fact. In fact, for him, it is a fact that we are not here having this conversation. And this, to me, is just so blatantly incomprehensible as a point of view. Do I have a quick minute to then say something about the Everett? Now, the Everett is, we're in the realism club. The realism is in without, it's not relative realism, it's just realism. And so I'm a qualified admirer of the Everett approach. But something I'd like to ask, something that David and Simon have talked about a lot over the years, is looking at the wave function. There is this wave function, and looking at structure in the wave function, and to see some sort of emergent structure of quasi-classical worlds. Now, it seems to me that if you look at the mathematical structure of the wave function, there is a much simpler way of finding structure that gives rise to quasi-classical worlds, and that is to simply look at the wave function in configuration space, to look at the gradient of the phase, and to identify a velocity field that corresponds to the conserved current in configuration space. And in effect, to say that in the wave function there is a set of parallel de Broglie-Bohm worlds, in effect many de Broglie-Bohm worlds in the wave function. And there is work showing that in certain limits related to decoherence type studies, that these de Broglie-Bohm trajectories become quasi-classical. It seems to me that the simplest realization of your program would be, you look at structure of the wave function and you would see that it contains many de Broglie-Bohm worlds. But then there is a final consequence, that these many de Broglie-Bohm worlds, they do not interact, they just evolve side by side. And here it seems then reasonable to invoke Occam's razor and to say, well, why not just say that one of these worlds is real, in which case you arrive at good old de Broglie-Bohm theory. So I would suggest that you're thinking that the simplest realization of your line of argument actually ends up at a single world de Broglie-Bohm theory.
Thank you. I think Carlo is next.
Okay, thanks. I am not going to answer. I'm going to continue along this line and make questions. I will answer then, I will try to answer to both of you. I think they're both very good questions, both of them. So, but let me do my role in questioning. And I have questioned Simon so much during my own talk that I'm not going to add anything. I hope to get some answer to what I said during my talk. So let me question Antony. So I have a question for Antony. The question is this. Antony, are you your particle that I'm seeing or the wave function which I'm seeing? I'm confused about that. I keep getting confused about that. I keep oscillating about that. When I get an answer to that, I get a very complicated, intricate answer from which I cannot come out.
Particles.
If it is the particle, why I just don't see the particle, and what do you mean that I can prepare the wave function? In a preparation, I prepare the particle. I see the particle is there. I only have access to the particles. Where is the wave function? If not, something I can guess. So it seems to me that if I have information about the particle, I see the particle, then the visible part of the debris bomb is a particle, and the part I don't see is a wave function. So the hidden part is a wave function, and I don't understand what is the point of having a wave function and consider probability of where the particle is. I should do the opposite. Given that I see the particle, I can give a probability distribution on possible wave functions. Somehow, the way you use it is always this game between, I know the wave function and therefore I have probability of the particle, but then I see the particle. I'm confused. Maybe it's my confusion. I like very much the cosmological stuff and the way of trying to go there and go out for the Born. But the ontological basis of that, I find it confusing.
Okay, thank you. Yeah, thank you. Super. Okay, David.
Okay, one sentence, quick reply to Antony. I think the answer would be if you had an Occam's razor move that let you eliminate the wave function entirely, that would be attractive. But of course, as long as you have a dualist ontology of corpuscles, particles plus wave function, it's not clear how the Occam's razor move is supposed to go, unless it's to somehow deny reality to the trajectories even while leaving them in the formalism, which I don't find persuasive for sort of post-Saunderian reasons, I guess. Here's a kind of broader thing I wanted to say, and this partly picks up on some of the discussion with Carlo. Let's just think what we're doing when we talk about interpretation of quantum mechanics. Think about classical mechanics for a minute, and think about what the interpretation of classical mechanics is. There's a sense in which it's totally uncontroversial. The classical state represents physical reality. What is that physical reality it represents? Well, there's almost nothing you're going to be able to say about that in full generality, because the space of classical theories is enormous. It contains n-particle theories, it contains solid-state systems, it contains field theories on a background space-time, it contains dynamical theories of space-time itself. So basically, there's almost nothing to say about the interpretation of classical mechanics other than it's representational. It allows me to tell a straightforward dynamical story about isolated systems where the state physically represents the goings on in the world. We wouldn't want to say that it says the state is real. That would be an ontological confusion. The state is a point in a state space that tracks the properties of reality. Which properties? Ask the particular theory. Don't ask classical mechanics in general to tell you any more than that. So in quantum mechanics, we need to remember the same level of diversity. We have the quantum mechanics of spin, we have the quantum mechanics of finitely many particles, we have the quantum mechanics of thermodynamic limits of systems, we have the quantum mechanics of fields on background space-time, we grope our way towards the quantum mechanics of space-time itself. What can you expect an interpretation of quantum mechanics in general to do? And the answer is going to be, again, it's not going to tell you anything more than very general claims about this. Here's the very general thing that the Everett interpretation will tell you about that. The physical state is, again, representational. The game is essentially the same as in classical mechanics. The world has physical features. Those physical features evolve according to their own dynamical equations. We can talk about isolated systems of the universe in isolation. We can write down dynamics for that. What are the physical features? Look at the particular theory. And then one way of putting the measurement problem from a kind of Everettian starting point is there's a prima facie worry that doesn't work. That at least in a lot of particular quantum theories, and maybe in all of them, somehow the strategy of just taking the quantum state as representational is going to fail you because of it predicts weird Schrödinger cat situations, or it can't handle the observed probabilistic evidence, or something like that. And then you might either say, well, look, here's another suitably general way to think about the ontologies of the theory, and to think about the interpretation of the theory, like Copenhagen, like relationalism, or alternately, the theory's wrong, and now we'll have to go back step by step through the various theories and see how they should be changed into different theories. But in looking at what the world is like according to the Everett interpretation, don't look for an answer except in extremely general terms, in entanglement, decoherence, branching, that abstracts away from a particular theory. You want to know what the world's like according to quantum mechanics? can't tell you anything at all. You want to know what the world's like according to the standard model of quantum field theory on a fixed background space-time? I'll give you an answer to that question. You want to know what the world's like according to the quantum mechanics of n particles? I'll give you a different answer to that question. The moves that say things like, according to the Everett interpretation, the wave function is physically real, everything is the wave function. This is a slightly confused way of thinking, and it's confusion that I've succumbed to myself in the past. So this rant, if you like, has myself as a partial target.
Thank you, David. Okay, Carlo.
I don't know if now or later, but I want to directly answer to that.
Okay, good.
Maybe later.
Good. Okay, well, I think we're going to throw it open to the floor. Very keen to hear from the floor. If you want to make a comment based on something that's already just been discussed, put up a finger. If you want to raise a new question, put up your hand. A familiar rule. So new topics, hands, additional fingers. You have a finger.
Can I perhaps make just a query, because I think we're each kind of thinking what we'd like to reply to what's been said.
Yeah.
I don't know about the other three, but if I then hear other questions, I'm then going to start forgetting what I wanted to say. Could we maybe have one round where we briefly reply, and then may I make that request? Or?
Gosh, well, so gentle they are. Yeah, Antony, go for it. I see a lot of people keen to remain silent. I'm surprised.
I'm just not going to remember.
Fine, you go for it. You go first.
No. I think Carlo, that would be too much.
Let's have a vote from the audience. Do you want to hear our answers, or do you want to pose other questions?
They all want to hear the answers. Carlo, you go ahead then. I think in reply to David, you wanted to say.
I want to react to what just David said, because I think there's a misunderstanding of the problem. Nobody asks to classical mechanics what is the world according to classical mechanics. But I ask to classical mechanics to the following: if I have a classical mechanic theory, like a free particle or harmonic oscillator, what is the world according to this theory? And the answer is not I have a phase space and this representational period, because they're numbers. The phase space, the position is given by a number, the velocity is given by a number. This number is a certain unit, represents something about the world, which I know what it represents about that particle, about that velocity. For instance, something useful to learn from Einstein. When you're in trouble, go operational, not because you want to be instrumentalist or because you want to be operationalist deeply, but because it clears your mind. It clears what you're talking about. So if I have a free particle, okay, the phase space has two coordinates, which is position and momentum velocity. And what is the position? The position is the particle is here, you put a ruler to see how distance is from your wall. So it's not, I don't want the world according to classical theory. I want the world according to one particular classical theory, what it represents. And the answer is you have not just phase space, but you have phase space with some coordinate phase space, which have an operational interpretation in terms of operation that you can do that give you a number. And then how these numbers evolve with time is what the machinery gives you. So the same question can be asked to quantum mechanics. And I don't want to know what is the world according to quantum mechanics. Of course I don't know what is the world according to quantum mechanics. I have to say which theory I'm going about. But if I have a quantum mechanical theory, what is the world according to that quantum mechanical theory? Now, it is my understanding that the world according to that quantum mechanical theory is not sufficiently described by a Hilbert space up to its symmetries and a Hamiltonian up to its symmetry. It's described by Hilbert space plus some specific sample joint operators which have exactly the same meaning as the preferred coordinate in classical theory. So X for Hilbert space as operator X or the operator P mean that I measure this distance. Okay, so the ontology that is given to me is not given to me by quantum mechanics, period. It's given me the structure of quantum mechanics tell me how a specific quantum theory, what is its ontology. And to get its ontology is not a state and a Hamiltonian. It's a state and a Hamiltonian and some self-adjoint operators whose spectra have to do with the possible result of measuring some distance and momentum and are interpreted in standard textbook quantum mechanics as interaction between something external and that system. Now, if you want to do many worlds, keeping all this machinery, then you have to be in many worlds the full machinery. Where are the spectra? Where are the interactions? Where is the operation? If you want to say many worlds, get rid of that. I think you're getting rid of the interpretation of quantum mechanics entirely. You're just if you want to say I keep all that, then you're just either in relation to quantum mechanics or in Bohr or in something else, or in a version of many worlds which I haven't seen yet. I haven't seen in your book. In your book, you in fact do that because every time you take a theory, you add something about it. But so you seem to be well aware of that,
I
right?
agree with virtually everything you've said so far.
Yeah, so you add something about it. But this is not never clear what this add is. What am I supposed to add? Is there an algebra of observable, and what does it mean exactly? If I have a wave function, suppose I'm going to do a free part. I have a wave function. It's a representation of what? I see a particle. Where is the particle? There's nothing in the Hilbert space and Hamiltonian that tell me that there's a particle and what is the distance from that wall. You say, well, but it's just a modulus square of the probability through some complicated things. But you have to tell me that there is a specific operator, and the specific operator in the interpretation has to come with an interaction with something else. Where is this stuff? I don't see this stuff.
Let's say something, David?
Sure, why not? Yeah. I mean, I think most of I think your version of the Everett interpretation is a
My
straw.
style is just Italian.
Yeah, no, of course. I think your version of the Everett interpretation is largely a straw man. I don't think there's any need to regard the Everett interpretation as somehow committed to simply Hilbert space plus movement in Hilbert space. One might try that as a further strategy, but the many worlds theory per se needn't have any engagement with that, and it's nowhere in Everett's description of it. To answer the question, let's follow the rules. Let's look at a particular theory. Let's look at a quantum field theory. So, what's the world like according to a classical field theory? Well, it assigns a hell of a lot of properties to space-time points. What's the world like according to, those properties are all collectively described by the point in the state space. Okay, so we want to do the same move for a quantum field theory. What are the properties that are all collectively described by that single point in Hilbert space? And the answer is a vast number of the properties you get by taking state, some operators, state, and those properties are spatially temporally located. So what are the properties? A very, very large number, many non-local properties that are being assigned to space-time points and n-tuples of space-time points. I have a vast, vast complex structure of properties of n-tuples of space-time points. Within that thing can be found a great deal of substructure. Many of those substructures look like classical field theories. That's the story for quantum field theory.
And could I just add a word here, because I think I failed to do this in my second talk and I really wanted to. These decoherent histories, what I was talking about, what is the structure? These are correlations among projections.
I know, but you have to choose projectors.
Yes.
And who chooses the projectors? The interaction with an observer.
You can get to...
Depend on the choice of the projector.
Of course, but any such choice of projectors will be a more or less interesting structure to the state.
So what is the physical interpretation of the choice of the projector, if not the standard one of the interaction with something else external?
Can I say, I think this term standard is really dangerous. I think it would be a good idea to have a moratorium on the standard interpretation.
Sorry, Copenhagen interpretation.
That too would be useful to have a moratorium on. People use that to mean many different things.
Messianic interpretation.
Say, or Dirac von Neumann, by all means. If you want to name check textbooks, that looks better, but the conventional here gets us into trouble.
Okay, Antony, you've been patient.
Yes.
And after this, we're going to open it to the floor.
I'll be brief. So I'll be brief. So my comment on the many worlds was that, well, why don't you look at structure in the wave function and identify a set of parallel de Broglie-Bohm trajectories as many de Broglie-Bohm worlds? That was step one. Then my step two was, well, then maybe Occam's razor, why not just have one world? So your reply seemed to be saying that, well, the second step, the Occam's razor, maybe there's something wrong with that because the wave function is still there, the structure is still... Okay, maybe. So what I'd be really most keenly interested is, well, from many worlds' point of view, why is the natural theory not a theory of many de Broglie-Bohm worlds? That would be my question, sort of slightly re-emphasized. In answer to Carlo, this business about the particles, the waves, let me maybe give a sort of concrete example. Let's say I'm in the lab. I have a container full of hydrogen atoms. They've just been sitting there for a long time, and what I'm going to do is I want to extract an electron from one of these atoms. I want to put it in a box, and I want to, quotes, prepare this in, say, the ground state of the box, and then do some experiments on it. Okay. And then I'm going to do this again with another electron. Pick another electron from a hydrogen atom, put it in another box, and repeat this, and then do statistics over these experiments. Now, when we say I am, quotes, prepare, I put the electron in this box, and I prepare its wave function in the ground state, what does it mean? What it means is, so preparation and measurement tends to be theory-laden. Okay, you need some understanding of physics and the laws of physics in order to know how to prepare and measure things. Here one would be assuming that there is a physical complex valued field on configuration space that obeys the Schrödinger equation. And if you want to know how to manipulate that field, you look at the Schrödinger equation and you ask it to tell you. And the Schrödinger equation tells you, well, if I change the Hamiltonian and in certain ways, the wave function will evolve in a certain way. You use that knowledge, assuming, there's an assumption here that this field exists, obeys this equation. You use that knowledge to prepare this ground state wave function for the particle in the box. Okay. Now, but then there's the question of, well, why can't I equally prepare a state where the particle is in the box, it has a ground state wave function that's spread over the box, it's a cosine squared, and the particle is here. Why can't I do that? Well, what will happen if you just look at how we would do this in the lab? I pick out if you just think it through in the de Broglie dynamics, I pick out an electron from that hydrogen atom, I put it in the box, and then I do the certain operations with the Hamiltonian to prepare the ground state. What you find is that at the end of this preparation, the actual position of the particle in the box depends on where the electron was inside the hydrogen atom at the beginning. Now, there was a hydrogen atom there. I did some process whereby I ejected the electron, put it in the box. Where the electron ends up in here depends on where it was initially in the hydrogen atom, but I don't know where it was initially in the hydrogen atom. And if these hydrogen atoms have been in this container a long time and been bouncing around and so on, the dynamics shows us that, well, things will relax. The distribution of electron positions in the hydrogen atom will almost certainly be equilibrium. So if I do this preparation many times, pick out an electron, put it in the box, prepare the ground state wave function, you can show quite straightforwardly that if the parent distribution of positions was equilibrium, then the prepared distribution will be equilibrium. So,
can't you just open the box and see where the electron is?
Well, you see, if you open the box and look at the electron, so you're switching on a Hamiltonian to interact with it, and that then affects the wave function. You can open the box and measure where the electron is,
so I do
and that will be an effective measurement where the wave function of the electron that was spread out will now separate into branches that are more localized. Okay? And what you will do, you will find yourself, the electron is near this position, it's somewhere inside this localized wave function. But you still don't know where inside that localized wave function it is.
Right. But
you know that it's somewhere in this localized wave function, but where in there you don't know. And the probability now for that will again be the Born rule.
when you talk about the wave function in this example,
I mean this sort of effective reduced wave function.
Or a branch of the wave function?
This would be a branch. Yeah, this would be a branch. Yeah,
so is it always a branch of the wave function you're talking about?
Well, basically, I mean, in any experiment, yes. I mean, the universe is complicated. There were certain various branches, and so I extracted this electron, and I mean, yes, there's certainly branching going on. So these are effective branches or effectively reduced wave functions that we're talking about. That's right. And inside, when you do this measurement, you create a more localized or reduced wave function. You know it's in there somewhere, but exactly where it is.
In reality, you are a crypto many world, because the wave function is, all the rest of the wave function is
got the wave function of the universe.
The rest of the wave function is a complex valued field in configuration space. It is not cats and tables and shit. But that's a separate conversation.
It just has the structure of cats and tables and shit.
Well,
okay. Well, thank you then for that answer. Now, I'd like to throw it open to the floor, and in fact, Philip Stamp would like to go first, I think.
I apologize for breaking in on this private discussion on the stage. I'd like to ask, I was kind of intrigued by the graph that Carlo showed, which was this comparison between well, I'm not sure if we should call them predictions of the Ashtekar group for, as a function of K, and a comparison with the spread that one can infer from current data. And now this looked rather nice. We actually had an attempt to, produce something that could, in principle, falsify the theory. Unfortunately, you then said, well, you weren't sure whether this was a hard prediction, which I was rather disappointed by. And I also was intrigued that you said that you were more interested in calculating the scattering of particles at the Planck scale. So my question is, what is so uninteresting to you about making hard experimental predictions and also making predictions that at the scale of the lab? I mean, I think the opinion of a lot of physicists would be that by taking refuge in cosmology, you're running away from the possibility that you might actually subject the theory to some kind of hard test. And I suppose this is a question which is more generally addressed to the panel. I mean, why cosmology?
I'll answer just with only a few words. I'm sorry if I gave this impression. My greatest hope in life right now would be to find a hard test to the theory. So everything that could get to that, I'm trying to go there. I have a understanding which I'm ready to change because I've changed at various times in the last 15 years. That it might be easier to find predictions in cosmology than in the lab or in astrophysics. There was a moment in which astrophysics seemed to open really a window. Then Lorentz invariants seemed to be a property of the theory, so boom. So maybe there is something unconscious in me that's scared away by testing. I don't know. But I hope no. I want strong predictions. About that particular one, it seemed to be the strongest available on the market, but just wanted to warn the audience that I didn't think it was strong enough yet to I mean, it's published, it's open to scrutiny, everybody can look at it. So absolutely, I mean, the game in quantum gravity is to not to produce a prediction, something this could happen, perhaps according to my theory, but this has to happen according to my theory. So then we can start ruling out theories. That's what we need. Lorentz invariant. Well, sorry.
So what has to happen if you have a superposition in which two substantial masses are in different positions according to your theory?
Definitely not what it's predicted by Roger or Penrose or.
Well, let's say that there are two entangled masses, so that we're doing an EPR.
Two separate masses.
Yeah.
I would say this is described by just standard quantum mechanics as they were interacting electrically.
So at any size scale?
Sorry?
At any scale?
Yeah, at any scale. So quantum mechanics is the theory, according to the theory, quantum mechanics continues to hold at any scale. Of course, more and more hidden by the environment, the coherence, by all things that we know, right? So harder and harder to pick it up from.
Okay, John Barrow has a finger on this, and so does David Wallace, and then Julian Barber has a question. And
it was following on from this last question about that observational prediction. I must have read that paper some while ago, but I can't remember the details. But I think it needs to be extended in a particular way, and that's because there are other ways to get, suppression or amplification of the power spectrum down at low L. I mean, most notably messing with the topology of the universe.
Yeah.
So that it's finite, maybe closed just with 3-sphere, or as the Paris group like to go for one of these, dodecahedral things. So that will produce the suppression. So it will be a good idea to redo that problem with loop quantum gravity with the topological constraint included, and see which wins out or whether it cancels out. I mean, for the outsiders, when you have a finite topology, you suppress the long wavelength waves in the perturbation spectrum because they can't fit in the finite space so easily. And so you get, rather naturally, some would argue, a suppression of that long wavelength signal. So by doing a new calculation with that included, that would be rather interesting. I mean, the way the results were going, though, was sort of suggesting that you might rule the theory out.
Yes, exactly.
Which will be a strong result.
Which will be wonderful.
Right, thank you, John. David, you had a finger on in answer to
Well, I
Philip.
thought I'd just pick up on Philip's kind of broader question, why cosmology? And I think, from the point of view of the Everett interpretation, no real reason. Handel's cosmology, fine, that was Everett's point to begin with, nothing to see here, move along. But why I think it's interesting, insofar as you think the Everett interpretation is fine, that's okay, the door's over there. More generally, though, I think cosmology is a good focus for worrying about the measurement problem if you're not lulled into Everettian complacency for two reasons. I think it's a test of the honesty of what you might call philosophically motivated moves that kind of particularly non-realist or crypto-realist ways of thinking. I mean, having to understand these things in physics of the whole universe type contexts is a good kind of honesty check that these things really work in generality. And I think for realist attempts to modify quantum mechanics and not just interpret it, then I think we're in this bind that quantum mechanics has been tested in a remarkably large range of interesting places. So I'm not sure I know a profound reason why, in general, one might expect to look to early universe cosmology to see places where this hypothetical replacement pulls away from quantum mechanics. I suppose the only thought would be, well, look, it's an exotic region we haven't looked in very much, whereas we've looked at other stuff an awful lot, and it's getting harder and harder and harder to look at bigger and bigger superpositions. So maybe there's a line of that kind there. But I'm not sure I have much more than that to say. I do think it does bring into focus, I suppose, the feeling that if you are going to modify quantum mechanics, there's some defeasible onus to modify it in a way that you can at least notice somewhere. So there would be an odd conspiracy in the world, I suppose, if quantum mechanics was wrong. We did need to modify it, but we really could modify it step by step, term by term, all the way up the hierarchy of theories through to string quantum cosmology or whatever. And in every step, the modification just remained a untestable alternative. That would be a fairly depressing situation. I think you talk to pretty much anyone who's an advocate of Bohm, for instance, and they will tend to say that it's not a positive feature of the theory insofar as it doesn't have any deviation anyway. It's attractive to think that somewhere it will pull us away towards different physics. I certainly get the impression that would be Antony's view.
Right, thank you, that's helpful. Julian, is your question about this topic of why cosmology?
This is a new issue.
A new issue.
Okay.
Well, just very briefly, in reply to Philip.
So about why cosmology. So if you think that quantum theory is a theory of an equilibrium state that arose from some past relaxation, then, and if this relaxation process is found by simulations to occur very quickly for ordinary systems, then you're pushed to just looking as far back in time as you can for some possible evidence of non-equilibrium. There are some other ideas I've had speculating that perhaps there's some exotic physics that can generate non-equilibrium from a prior equilibrium state involving gravity, perhaps black hole evaporation, pure to mixed transitions, maybe Planck scale physics. There could be some new physics we could generate non-equilibrium. But if you leave that aside, in this theory it seems certain that once you're in equilibrium, you're stuck there. And so one is just pushed, by virtue of the logic of the theory to look as far back in time as you can, and you end up looking at the early universe.
Thank you.
Could I make a comment to
Does that not make sense?
Okay, well, there's a finger from Simon and from John, but be very quick because Julian has been so patient.
Well, I'll just be very quick. I mean, why cosmology? One reason is cosmology is the closed system par excellence. and one may well think
You mean
that...
topology or cosmology?
Well, that's... I would love to talk to you about that, but I've only got a second here from Jeremy, so let me be quick. So a closed system par excellence, and quantum mechanics has always, in conventional formulations anyway, been stated as a theory that requires an external system. So there's a very straightforward challenge coming from cosmology in that way, which Carlo, I think, is responding to, but I haven't understood quite why the prohibition still seems to apply.
Okay, John?
Do you worry about more fundamental problems with physics and, say, the idea of equilibrium you're talking about? When you're sort of within 1% of the Planck temperature, people seem to be taking over standard statistical mechanics. There's only about 10 or 100 particles in the horizon. It's not clear that any of these ideas about statistical equilibrium are really holding terribly good back then. The horizon is very small, and if you just had the ordinary Planck radiation spectrum, all the long wavelength parts cut off. It's outside the horizon, and you don't have the ordinary calculation of the black body constant, a different value. So lots of things that are not quantum gravity things are messed up when you get to that very high energy.
Yeah.
And so it could be a reason why you necessarily have deviation from equilibrium, that you just don't have room inside the horizon for the whole spectrum of the states that you need.
So that's a good point. I'll just say in one sentence that this, I use the word equilibrium. The kind of equilibrium I'm talking about is not really thermal equilibrium. There are analogies. This is an equilibrium of a probability distribution in configuration space. The equilibrium distribution is mod psi squared. But still, maybe something to think about. But there is, the equilibrium I'm talking about is not really thermal equilibrium.
Right. Thank you. Okay.
So you needed to say what you mean by temperature.
Yes, that is correct. That is right. That is right. So that is a good point. Yes.
Julian Barber?
Well, I'd like to have a little go at Carlo, if I may. I think you have a tendency to unjustifiably atomize the world, Carlo. You talked about just local interactions, but that's only part of general relativity. A key part of general relativity are the constraints. The constraints hold, Carol Kukoc calls them laws of the instant, and they literally hold through the whole along a space-time hypersurface. So I'm a little bit concerned about just thinking in terms of general relativity, that it's about local little bits interacting. Then there is the fact that it seems to me your starting ontology is actually to break up the classical gravitational field into atoms, which are very like, for me, Lucretius. This is atoms moving through the void. You have spin networks, which are not spin networks as Roger Penrose created them, which are purely combinatorial, but they are embedded, is my understanding. And they have to be embedded in three-dimensional bare manifold. And as far as I understand it, it can be any dimension, that manifold. But the embedding to define your Hilbert space seems to be very crucial. And then when you talk about these nice little systems, and you've just got your one particle system, and you've got I think it's misleading to say it's all very nice and easy to define the operators and things like that, because we're sitting in a room where the walls are not moving relative to each other, and you've got a reassuring ball pen in your hand where you can say, yes, this is the distance, it's along like that. If you lived in a swarm of bees and there weren't any things like that, the matter would be infinitely harder. And I think this is just actually, if I may say so, being swept under the carpet.
Okay, these are 4 questions, so let me answer rapidly to all of them. First, about the locality of the constraints. I think one should not confuse the locality of the equation from the locality of the solution. The constraints of general relativity have the same locality as the Gauss law of the electromagnetism, which is a local equation. course, if you fix a gauge and you want to solve the Gauss law computing, for instance, the electric field as a function of the charge distribution, then the solution is non-local. But no physicist would say that the Maxwell equations fail to be local because there is a constraint. And I think, in the same sense, no physicist would say that the Einstein equations aren't local in an appropriate sense. Of course, if you manipulate the theory, bringing it by gauge fixing into bringing non-locality, then it's non-local. But there's your manipulation; it's not the equation. So I stand on the fact that the equations, the electromagnetic and the gravitational interactions are local, which is a common point of view in physics. The second thing is about the spin network being embedded in space-time. And here
in the bare manifold, I said.
In the manifold, sorry. And here the answer is no. The actual construction of the theory has gone through various phases. So if you want to point out some old papers in which it was the case, in fact, it's true. But if you take, I don't know, my last review of big Zakopane lectures, these graphs are just defined combinatorially, so just a set of a set and links. So there's no embedding whatsoever in three-dimensional space that has any physical. And in fact, what had happened historically to the theory is that at the beginning there was an embedding, and then people realized that this was not playing any role there, so it was dropped. But that's not part of the theory, and I think it's a correct move, in a sense, for the reason you were pointing out. The third point was about the difficulty of giving an interpretation to the operators, and I think my answer is David's answer. So it's we are not giving an interpretation to any possible observable in any possible quantum theory. We have to take a quantum theory, and within this quantum theory, we can use operationalism as a help, not as an instrumentalist philosophical position, to tell what things are. So if I'm doing a non-relativistic quantum theory, it means that I assume I have walls and I measure distance from the walls, maybe not with a rod, but with something a little bit smarter. If I'm doing general relativity, I know what are the observables in general relativity. Are the quantities that our friends in astrophysical department measure when they do a relativistic picture of solar system, or when they do use general relativity for cosmology. So there are observable quantities, and how I know what is the phase space of general relativity. I might not know how to write explicit and observable, but I know exactly what I mean in connecting theoretical quantities with observations. It might be a long story because there's different variants, of course, but we know how to deal with this story. So what I insist is that in the classical theory, I'm not just giving equation, I'm just giving interpreted equation, namely connecting these quantities there with machines that I can measure, and this gives me how to use it concretely. And I want to say that in the quantum theory I need the same. I need a list of operators in the quantum theory which correspond to things I can measure. Concretely in quantum gravity, these are the J operators, which correspond to triads, out of which you can construct gauge-invariant things, which are the measurable ones.
Well, one follow-up question. I'd like to understand better about how you get away from the embedding. That would be fine, thanks. But what about the role of the inertia parameter in the emergence of the inertia parameter? What role does it play now in the area and volume operators?
It's there, and it's. In fact, there's big open discussion about that. But let me give you the standard answer. The party line so far. The party line may evolve. Let me give you the party line. It's similar to the theta QCD. To the theta angle in QCD. So it's a parameter that might enter the classical action, but has no effect on the classical equation of motion. However, it has effect on the quantum theory, and in fact, it affects the spectra. It affects uniformly the spectra, so the spectra are proportional to gamma. Recently, there have been a number of people who are arguing that it has to be essentially one for some reason of consistency. So far, it has been considered a free parameter that enters the quantum theory and is not visible in the classical theory. So the theory, in fact, depends on cosmological constants, Planck scale, which you can put equal to 1, and a free parameter. So there are two-dimensionless parameters in the theory.
Thank you. Okay, now we've only got a minute left, but have not seen a great many ardent hands or fingers, but I'd like to ask us to end with Cormac Rafferty's question, whatever it might be.
If I may, it's more in the way of a philosophical comment / question on the relational view versus the others. It struck me, especially during the first discussion, but also there, that it really is, and this is really, I'm asking rather than commenting this, but it really seems to me to be very much an echo in some ways of a very old debate, which is, Heisenberg's dismay at the wave function. For Heisenberg, I think he would be in Carlos's chair arguing that quantum theory is about discreteness, and his big fear about the wave function was that it was fine as a mathematical tool, but physicists would be led down the path of spending a long time trying to figure out what it actually meant, what it really, did it have a physical significance or not. That was his fear, and it just struck me that it's almost, there were echoes of that debate today. But can I just add to that I know many worlders wouldn't see Schrödinger as a natural ally because of his objection to the to state collapse, etc. But in fact, and this is a question for Simon, I don't think that's quite right, is it? In recent years, several people have claimed that long after the Cat paper and so on and so forth, he actually came around to a slightly modified point of view where he does talk about several states. Somehow he does it without talking about state collapse. And that I've heard that many worlders, some of you are now saying that was actually a predecessor. Could you say a little bit about that, maybe?
Yeah, and interestingly, Schrödinger's thinking on that point took place here in Oxford. Something in the water. But yes, I think that it's something actually that Roger once said to me. Look, I thought of many worlds back in the mid-50s, late 50s, I think. Everybody did. It was not so hard to go from the Schrödinger-Cat paradox to the idea that the macroscopic superposition exists. Whether that gets connected with the further thought that, and indeed it would not be observable as such, because the observer would become entangled with the system and would themselves then, my Galileo's sort of dictum really, put the observer into the physical dynamical theory. So whether that further thought occurred to many people or not, I don't know. But I think Schrödinger certainly did play with the idea that the unitary evolution holds universally. David Deutsch made this rather pointed comment. Schrödinger once said, "I fear you will think I am mad," something like that, for taking the Schrödinger equation seriously. And Deutsch made the comment that what a state has physics come to, where a man gets a Nobel Prize for an equation, but then is in fear of taking it seriously. An extraordinary turn of events, that is.
Can I take 2 of these 3 minutes, or then?
Well,
one of these 3 minutes?
Gentlemen, you don't wish to make a closing statement particularly?
Yeah. No, I'd like to hear closing answers.
Okay.
Okay, so I'm not making any closing statement, I'm making answers. I'm sure there will not be closing answers. Anthony asks, Carlo, some super intelligent in the future is believing that you are not here because in his wave function you are superimposed and there is no fact of the matter here. Does this bother you? I think it doesn't, because it's exactly the kind of things that happens in theoretical physics all the time. I think it's very similar to what happens in special relativity. If I take Einstein's simultaneity convention, right now in Andromeda there is something which has already happened with respect to the, not the past but the simultaneity convention, with respect to which I haven't happened yet, with respect to his... this makes no sense whatsoever. but that's the structure of the world. I mean, the relation between when things happen for who are complicated. I think with this guy in the future, I could talk if I survive until him. I can talk to him and we would agree. And the fact that now for him, in the future, before I interact with him, there is a discrepancy in what we see, it doesn't me bother. I know that you would have something to object to that.
But for him,
let me
I mean, there wouldn't be a fact of the matter about the past.
That's right. I think there are fact of them. Simon objection are two. First of all, why not Galileo principle of bringing the observer into the picture? And the other one is why this forbidding this deviator, this law that forbids self-representation. The second one is a hard question. The first one, I might claim that that's exactly what I'm doing, because I am bringing the observer into the picture, and I'm just saying that the observer can be represented quantum mechanically, and the fact of the matter that it has information about something is given by the correlation between the two. You would agree on that. Only that there is a fact of the matter for him about what he knows, and there is a non-fact of the matter with respect to an external. So I'm not erasing the possibility of describing the... I know what I mean, that I have information about you, both in terms of for me and in terms of somebody else seems to the side. I'm just disconnected the two. The second question is much harder, and I mean I could go out with an easy answer, say, well, I mean, if I really want to give a description of myself in which I include myself as a system, I just could imagine what I could measure if I was not myself, and then somehow. But I think that would not be a satisfactory answer, so I keep it as a challenge. Where does this prohibition to self-representation come from? I think it's a good question. I'll stop here.
Okay, thank you. Thank you very much. Well, gentlemen, I think we need to stop, if that's all right. Afraid. Ladies and gentlemen, I hope I haven't cut off anybody who was ardent to ask a question. Please catch a speaker if you wish to as we walk out. Before we go, may I say, first of all, as you probably know, this is part of an ongoing series of 2-3 day events. In early December here in Oxford, there'll be another one with the general area of anthropic principle and fine-tuning in the foundations of cosmology. I think it's December the 2nd to the 5th, something like that. After that, there will be Constants of Nature on March, I think, 18, 19, 20 in Cambridge. So, but watch the website for the exact dates. I'm not quite sure of those dates. Finally, I'd like to obviously ask you to join me in the traditional way of thanking the speakers, but I'd also like to ask you to join me in thanking the local organisers and St Anne's College, especially Chris Doog and Khalil Cham, and also indeed the technical staff who've made the video production. So thank you very much.